I'm Alex Bray, and this is Lab 5, Motion of Falling Objects. I'm in Lab Section MO5. I observed a football, which is my fast-falling object, and a paper ball, which is my slow-falling object. The objective of this lab was to determine how the force of gravity and drag are related in calculating net force and thus position. The main result I found in my lab was that the force of drag is a necessary component in calculating the net force of a falling object to predict its motion. Without drag, the calculation of an object's predicted position does not take into account any air resistance that it will encounter, and its velocity will keep increasing with time. So here's my tracker video. Here's the football and the paper ball. I set the grid lines to about to where their origin was. I used this stool in the background as the calibration stick, which was 0.37 meters. And there's the objects falling with time. The time between each clip of the video is about 1/30th of a second, and it came up with this data that I extracted from the tracker video. The blue is the position of the slow object, and the red is the position of the fast object. The fast object falls faster because it encounters less drag resistance than does the slow object. And so to model this, I set the initial conditions for the mass of the paper ball as 0.0045 kilograms. Its initial position was negative 0.00655 at y, so it was just below the y-axis, and it started at rest of velocity is 0, 0, 0. The delta t, like I said, is 1/30th of a second because that was the time between each clip. For the fast falling object, the mass of the football is 0.397 kilograms. The football started just above the y-axis, so its initial y position is 0.0590, and it also started from rest, so its initial velocity is 0, 0, 0, and 1/30th is delta t. So here's my code for these objects. The time of the video was 0.567 seconds. Factored in the force of gravity, 9.81 meters per second. The force of gravity is just in the negative y direction, so it's the ball's mass times the force of gravity, the absolute magnitude of the force of gravity. The net force is only equal to the force of gravity in this case because we're not factoring in the drag force yet. And the prediction of the new velocity and position of the object are based on Newton's second law, and the object should fall at the same speed because mass cancels out in this formula because F net includes the ball's mass, so they should cancel out, which leaves only the force of gravity, which is constant, times delta t. The arrow gives the position of the force of gravity, and this advances the clock from time 0 to the time steps specified, which was 1/30th of a second. And so here's a run of the slow object without drag, and a run of the fast object without drag, and the second plot that I have coordinates both the fast and slow object that was measured in the tracker video as the blue and red, and the green and purple is the objects from my model without drag. The models for both the slow and fast object are almost the exact same because the only acting force is that of gravity, negative 9.81 meters per second, because the masses cancel out, like I said earlier, in the position to find the new velocity in the code. The only reason they're slightly different is just due to slightly different initial positions. And then for my code with drag, this is the code for drag. B is found experimentally by matching the final position of the actual recorded data to the final position of the model by running the model repeatedly, so it's a trial and error experiment. And this is the new net force of the net force, and it includes the force of drag, and the second arrow down here now indicates the force of drag, so it should be in the positive y direction. And here is a run of these models. This is the run of the model, the slow object with drag, and the fast object with drag. And here's a graph of the objects with drag. The blue is the actual slow object extracted from the tracker video, and the red is the model of the object with drag, so you can see it is extremely accurate in predicting position. And the same thing for the fast object. Blue is the actual fast object that was extracted from tracker, and the red is the model of the fast object with drag, and it is also extremely accurate. To answer the what does it mean question, for the object that drops slowly, examine the velocity versus time predicted by the models with and without drag. Which model, if any, predicted terminal velocity? So the blue is the run of my model of the slow object with no drag, and the red is the run of the model of the slow object with drag. And the model of the slow object with drag predicts the terminal velocity, while the model without drag does not. This is because as time increases, the force of the drag will eventually equal out with the force of gravity to make velocity constant. Without the force of drag, the velocity keeps increasing in the negative direction, and thus there is no terminal velocity. To answer the what if question, for the object that drops slowly, use your models both with and without drag to examine the object's velocity as a function of time in the case where the object is thrown downward initially instead of dropped from rest. In this case, does the object reach terminal velocity? And then examine both models and compare terminal velocities if any are found. So in my code for the initial conditions, the only thing I changed was for the y component, I just set it equal to -1 to give it an initial velocity. And this is the graph that it came up with. The blue is the slow object with no drag but with an initial velocity, and the red is the slow object with drag and with initial velocity. So the only difference between it and the and not having an initial velocity is just how far down the y-axis it goes, but the rate basically stays the same. The object with no drag still has no terminal velocity because only the force of gravity is present, and so the net force keeps increasing as time increases, thus increasing the velocity. And the object with drag still has the terminal velocity just like when it had no initial velocity. This terminal velocity is now larger due to the effect of the initial velocity in the following equation to find the updated velocity as such, because the initial velocity is now present as -1.